everyone. And thanks everyone for sticking around. I'm hoping to use the rest of the time to chat about some basic statistics with you all. We will be going a little bit quick, but don't worry, you don't have to kind of worry about the detail of it today. I kind of just want to give you a foundation as we wrap this course up so that you're able to take these skills kind of beyond the course. I will go ahead and share my screen over here. All right. So over here, I've got my R notebook open. As I said, we'll be talking about basic statistical analysis. Please feel free to ask questions. I see there's one in the chat already about having a module and quiz of this session uploaded as well. I believe yes. So these are all kind of the statistics bit I'm going through now is exactly the statistics module that will be uploaded later. So we can start for anyone who has no background previously in statistics. It's one of those things that sounds a little bit intense, but really we have been doing a lot of it already in this course. It's just a tool to help us analyze data, things as simple as mean, median, mode. That's all statistics. But basically the idea is that statistics help us gain a better understanding of the trends in our data, and then what might be more interesting or meaningful than others. So I'll start off talking about something. We'll make a difference. We'll differentiate between descriptive statistics, inferential statistics, and beyond. So descriptive statistics, which is what I'll start off talking about, just helps us simply summarize our data. So it describes what our data looks like. And it's best illustrated with an example. So here I'm going to run this code chunk over here. But yeah, so descriptive statistics help us summarize our data. So over here, I'm running this code chunk. So this you might have seen before in previous examples where loading some handy packages like Rio here, Tidyverse. There's some new packages you might not have seen, but those are some things we will use today and you'll see exactly how it's used. Here I'm anchoring the code. This is something that a little trick that we used in previous sessions where we say we're using the here package and saying here I am. And this is the name of my coding document. So this basically locates where my code is and makes everything relative to that. And finally, we're importing the HIV data set that we always use. So if I run that, now I have this HIV data set that will look familiar to you. This you've seen before. So one of the simplest ways to get some descriptive statistics is just using the summary function, which I think you've also used before. So if I run the summary function, for any column that is numeric, so any column that has numbers, the summary function will print out some basic statistics for me. So it prints out the minimum, maximum. It also prints out the first quartile, third quartile. So over here, the difference between these two gives you something called the interquartile range. There's also the median and the mean. So these are all summary statistics, and it's quite useful just to see this right off the bat with our data. And there's a very simple way of printing out some statistics. So we can see some important measures of each numeric variable using this. However, there are other ways you can get these values. For example, this rstatics package allows us to print out similar values as well. But the way you do it looks a little bit different. So up here, we simply ran summary with HIV data. But over here, now we're going to say HIV data, pipe operator, get summary stats, type common. And we can see what happens when we remove type common. So over here, it creates a nice little table for us. Each row represents a different variable in our data set. It tells us how many observations we have for each one, or how many non-blank observations, I should say, or how many complete observations we have. It also tells us the minimum and maximum for each one, median, interquartile range, mean, standard deviation, standard error, and then the width of the confidence interval, I believe is this last one. If we remove this and just run get summary stats, it'll print out some more extra ones. So Q1, Q3, I'm not really sure what MAD is, but you can see it prints out quite a bit. But if you Google get summary stats, you'll be able to see, oh, over here, even in the pop-up, it shows different. You can say full, common, robust, 5-number. You can kind of pick and choose what you want it to. So if I just said median IQR, it would just print out median and IQR, and N refers to the number of complete observations. So that's also a really, really handy function to work with. So I'd encourage people to use get summary stats from the rstatics package as well. So here in the module itself, once you're comfortable, you can try some different exercises. You can try printing out only mean and standard deviation for age and gender, and only median and interquartile range for all variables except ID. This is just some exercises for people to try on their own time, just to get you used to using summary stats, but also by focusing only on certain values in certain columns, you'll have to filter the data set first or select variables in the data set and then work with those columns only. But like everything in R, there's yet another way to print out descriptive statistics. This you will have seen a couple of modules ago when we did our data analysis pipeline. We can simply use tidyverse coding and print out descriptive statistics as well using this summarize function. So I'll explain what's happening in the code chunk below. So first, we're looking at our HIV data set. Now we're coding gender. I think this might have been reversed. I think 1 is actually female and 2 might be male. So here we're creating a variable called gender coded. We're saying the case when gender is equal to 1, coded as female, when gender is equal to 2, coded as male. And if it's ever anything else, this is just a good catch to put in. If it's anything else other than 1 or 2, just replace it with a blank. I like to put that in as a catch, just in case there's something strange going on in my data and there's an unexpected value. This will just make sure to turn all those unexpected values into blanks. Then we select only the variables we want to work with. So over here, we want to know, for example, if we want to know age and gender coded, then we select those variables. Then we can group our data by gender, because if we want to know median and interquartile range of age by gender, we can group it by that variable. And then finally, we summarize. So we create a new column called median age, and that calculates the median of the age column. And finally, a column called IQR, or interquartile range. And this function helps calculate the interquartile range of that variable. So when I run this, we get a little table like this to say median age between males and females. And you can also see interquartile range of age between males and females. This is another handy way of printing out some basic summary statistics. Of course, it has a few more steps that are involved, but once you kind of get used to doing this step by step, you can really change this to kind of suit your needs and code, print out what you want it to print out. So there's also another package that enables something similar. It's called the GT summary package, and I'll show you exactly how it works. So for example, if we do the exact same thing we did above, we go into the HIV data set, we add a variable for coded gender. Again, let me change this. And this looks the exact same up as before, right? So we're creating a new variable called gender coded. We're saying when gender equals 1, coded as female, and when gender equals 2, coded as male. And then we have this little default catch for anything else that doesn't match those two values. And again, we're only selecting the variables we want to work with, which is age and gender coded. The only difference is instead of up here, so up here we used something called summarize, right? We created something to summarize I know it says mean and standard deviation, median and IQR of age. So instead of summarizing, now we're doing something a little bit different. We're using this GT summary package, and we're using a function called TBL summary or table summary. And we want to separate values by gender. Now, if we summarize by gender, we get something that looks actually pretty professional. Like something like this would go into a publication. And now you can imagine if you have a lot of other variables. Let's say if we had, what if we had our other variables in here, like HIV, CD4, and viral load. Let's see what happens when we do this, when we add these guys. Look at that. Now that we've added these guys, now we've got two columns, females, and it tells us how many patients are female, it tells us how many patients are male, and it even tells us that it's printing out either for continuous variables, it'll print out the median IQR, and for others, it'll print out N percentage. So over here, we can say 66 females have HIV, 77 males have HIV. And you can see there's the unknown. So automatically, if something is blank, it'll put it as unknown. So that's how it calculates. And it's a really good table summary is often used when you're writing a publication, for example. I always use table summary for mine because I like the way that it prints out tables. There are lots of ways you can customize this. For example, I wonder if I can show you another code. I think maybe pediatrics analysis. Actually, let me open it up for you from my other project so you can see what some of the complex tables can look like. Give me a moment. Yep. Sometimes this is for another project that I'm working on, just to show you what, if you have a bigger data set, what it can look like. So this is a very handy, so often in publications, you'll see, particularly publications that are involving hospital patient data, you often have a table that describes the patients that you're working with in your data set. So this is one of the patient data sets that I got to work with. And over here, we can see what it looks like. I see Leah has a question. Is the unknown on the summary table always due to missing, or could it be that it was non-numerical? So usually if it's non-numerical, it still will print it out. So for example, over here, sex in this data set, sex was non-numerical. So it only included observations such as male and female. So only if it's blank will it print out the value unknown. So unknown just replaces blanks, regardless of whether the variable is numerical or non-numerical. That's just to show you what a longer version of that table looks like. I think you can also replace unknowns. So it prints out unknowns for blanks by default, but you can change what it says to something else. And we can actually maybe see how to do it. Table summary, replace unknown with another term. Let's see. Yeah, here it's printing unknown. But here they've changed it to missing. But there are different ways. Yeah, it looks like you can customize it. So it's not that it always has to say unknown. You can change it to say something else other than unknown. Yes, a very, very handy tool. But I hope that answers your question, Leah. Oh, I forgot I provided this link. I think this provides some good, it's a good tutorial for this particular function. So it kind of shows you some basic usage like we just did, and then fancy things that you can do with it. You'll see in this tutorial, they use a weird version of the pipe operator. This also works, but this weird looking thing over here is just a pipe operator. You can see they've also added P. So if we were to add P here, this, let's see if it'll work. We add P, this should give us, there we go. So this tells us, the p-value basically tells us if there's any differences between females and males in this data set. And you can see the p-value is pretty large, so there is no difference. But hold on to that for a second, because I will talk about p-values in more detail. Okay. So what we just saw was descriptive statistics. So as I said, descriptive statistics just basically makes us take a closer look at our data set, understand trends in our data set. But what we just did above here, right? We added a column for p-value, and p-value is relevant in comparing females in our data set to males in our data set. So as soon as we start comparing things or seeing if there are important differences in our patients, then we're moving on to something called inferential statistics. So for example, in scenarios with health data, you might, perhaps in our HIV data set, suppose there was an additional column showing prophylaxis or some sort of treatment or antiretroviral treatment for HIV. And we were trying to compare those patients who were on ART versus those who weren't. And what we wanted to see if viral load was significantly different between patients who were on ART versus those who weren't. Something like that would be a question that inferential statistics could help us answer. And it is quite relevant to a lot of healthcare data sets, because often in healthcare, we're concerned with things like treatments or vaccinations, and seeing what interventions are actually useful in changing somebody's health outcomes versus what interventions might not be useful. So the way we can do that in its most basic sense is by performing something called a statistical test. There are several different statistical tests out there, and which one we use depends on what our data looks like. Today, I'm going to talk about two simple ones that it's quite easy to tell the difference between. So something called a t-test that you may have heard of before. T-tests are used when we're comparing continuous variables, whereas something called a chi-squared test is used when we're comparing categorical variables. As I said, there are a whole bunch of other statistical tests, but for today, we are just going to cover these two. And for these two, R actually has a really handily built-in function for both t-tests and chi-squared tests. We'll start off with the t-test. So how we use this function depends on how we structure something called a null and alternative hypothesis. This sounds super statsy. In simple words, a null hypothesis is the default scenario where we assume there's no difference. So for example, in our previous example over here, our null hypothesis, if we're just looking at age, we would assume there's no difference in age between males and females, right? We'd say male patients in our data set are around the same age as female patients in our data set. And in mathematical notation, this is how it would look. So we say H0, which is our null hypothesis, is mean age male equals mean age female. And that's default. We just assume there's no difference. On the other hand, we also have to create something called an alternative hypothesis, denoted as HA. And this depends on what we're actually interested in. So this is where your clinical sort of expertise comes in. And this is where you often require clinical context for the statistical question that you are asking. So for example, our alternative hypothesis could be very general, just saying that mean age among males is not equal to mean age among females. Or it can be a little bit more specific to say mean age among males is bigger or larger than females, or vice versa, that it's smaller or equal to females. As I said, which one of these three we choose depends on prior knowledge. Often, if we have no prior knowledge, it's usually safe to just go with the first one. So just to say simply mean age male is not equal to mean age female, which is something called a two-tailed hypothesis. This is because it has two different options, right? Mean age among male patients can either be less than or greater than female patients. So then finally, if we pick that one, the hypothesis that we're testing can be noted like this. Oop. This is how you'd note it in sort of mathematical terms to say the null hypothesis or the default is that age is equivalent between males and females. And then the alternative hypothesis that we're quote unquote testing is that it's different. There's one other thing we usually have to specify in R, and that is whether or not the two samples we are comparing are paired. So what I mean by paired is that if they are the same patients, for example, if you're comparing patient weight before and after a procedure, and you wanted to see if that procedure significantly impacted weight before and after, your data would be paired because it's the same patients you're measuring before and after. But over here, we're comparing two samples of different patients, so they're not paired. I hope that makes sense. So if we're comparing patient weight before and after a procedure, it is paired because you're comparing two samples of the same patients. But over here, we are not comparing two samples of the same patients. These are patients that are different from each other, so it's not paired. So we'll see how this works in practice. So here, this is me just creating a vector for male and female age. There are other ways to do this. This is just one of them. So here I'm going into the HIV data set. I'm filtering female patients, which actually I think is gender equals 1. And I'm saying select age, and this pull thing just helps us pull it into a vector. So when I run this, it'll create something on this side. So it'll create, actually, let me print it out here. So if I print out female age into a vector, it just prints out all of the ages of female patients in my data set. And then I do the same for male age. So I can see in my environment, I have female age and male age. And then we do a t-test. So as I said, R has a function called te.test. It doesn't really matter what you put in X or Y, just as long as one of your columns is in X and one is in Y. So here I've said female age is X, male is Y, but we could quite easily do the opposite. I have to specify what my alternative hypothesis is. So if you remember up here, we decided we would use this first one, the generic one, which is called two-tailed hypothesis. So I've put, where are we? So I've put two-sided over here. And then finally, I've said paired equals false because I'm comparing two different samples of patients rather than two of the same samples or two of the same patients. So I run this, I get something that looks like a little paragraph of information. So let's take a look at this. You don't have to worry about everything here, but there's a few important pieces of information. So the first one is a p-value, which is something I mentioned earlier. So a p-value is often a measure of significance. So when somebody asks you if something is statistically significant, they're often referring to a p-value. Now, there are a lot of criticisms of using p-values. Often we like to use p-values in combination with 95% confidence intervals to actually mean something. But for now, let's just focus on a p-value, which is over here. So typically, a p-value of less than 0.05 would mean that we can reject the null hypothesis. What that means is that we can actually say that there is a difference in means in age. So if we had a p-value that was really small, we could say, yeah, the male patients are either older or younger than the female patients. We'd be able to say that confidently. But here we have a really big p-value. So we're not able to say that. So we're not able to say that there is a difference in means or a difference in mean age. So then there's a 95% confidence interval, which is over here, which goes from about -2 to +2. So confidence intervals, this is a confidence interval for the difference in means between male and female patient age. So because it passes through 0, it's hard for us to say whether there's a true difference in mean age between these two samples. So basically what the confidence interval is telling you is that the difference in age between females and males can be as little as, so males can either be 2 years younger than female patients or 2 years older. And that doesn't tell us anything, right? We can't say if they're in general older or younger. They can be either younger or older. It's not giving us any information. So we cannot say that there is a true difference in means. And finally, there's two other helpful pieces of information here, which is mean of X and mean of Y, which is down here. So this actually shows us the mean age in each group. And you can see it's basically the same. So, and it actually does tell you here, alternative hypothesis, true difference in means is not equal to 0. And because our p-value was huge, because our confidence interval overlapped 0, and because these two means are very, very close to each other, we cannot conclude that there is any statistically significant difference in patient age between male and female patients. So that is the sentence that is sort of the conclusion that we can draw. I'll pause for a second there just to see if there's any questions about this. There's a lot of terminology that's pretty specific to statistics, but hopefully it's clear kind of what a t-test is, what a p-value is. But I'll pause for a second to see if there's any questions. Please feel free to pop them into the chat, or you can raise your hand also. I see Leah has a question in the Q&A. So if a character was input in a numerical variable, how would that display in the summary table? If I understand that correctly, so in the summary table, a numerical variable is always displayed with a median and interquartile range. So if something is a numerical variable, it would always display as such. But if it's I see Leah's come, please feel free to raise your hand and ask your question.
Can you hear me?
Yes, I can hear you.
Thank you. So I wanted to know if in a numeric variable, there is a mix of a character, like a wrong entry.
Okay.
Yeah. How would that display in the summary table?
So that if there's a wrong entry in a numerical variable, it automatically converts the entire column into a character variable. So it would display as a character. So it would have different categories kind of based on that character variable. So as soon as there is a mistake in a numeric variable, it automatically converts the whole thing into a character. And then so you'd have to do some data cleaning in advance to turn it into a numeric variable. I hope that helps answer.
Yeah, that's all right. Thank you so much.
All right, no problem. And I see Chioma also has a question. Could you please go over the significance of the p-value again? Yes, I can. So over here, so a p-value basically indicates something called statistical significance. There's some math behind exactly how a p-value is calculated, but for now you can understand it as a measure of significance. So it exists between 0 and 1. So basically a p-value closer to 0 is better, and a p-value closer to 1 is worse in terms of significance. So p-value closer to 0 would mean actually there is a significant difference between our two samples. So in this case, our two samples are female age and male age. So if we had a really, really low p-value, then we can say, actually, yes, female age and male age are different. But a p-value closer to 1, so a p-value that's higher, doesn't allow us to say that. So it actually says, actually, female age and male age are pretty similar to each other if p-value is large. So, and typically the threshold it's quite low. So the threshold is 0.05. And any p-value less than 0.05, people often say that that is statistically significant. So for example, if we had a p-value of 0.04 here, we would be able to say that there is a statistically significant difference in female age and male age. But because that's not the case, we aren't able to come to that conclusion. I hope that helps answer the question, but feel free to raise your hand or pop something in the chat if it's still unclear. Oh, yep. I see. You can go ahead.
Sorry, the p-value, there's a range for it. So if the p-value is closer to 0, it means that you can say there's no statistical difference between the two variables.
It's actually the opposite. So the closer it is to 0, specifically if it's less than 0.05, that means it is statistically significant. But the higher it is, the worse it is. So the higher p-value means there is no significant difference.
Okay.
Yeah.
Okay. Thank
So
you.
it's kind of, no problem, no problem. It is a little bit counterintuitive. So a smaller p-value is better and a bigger p-value is worse if what you're looking for is a statistically significant difference. So usually in your data, you look for small p-values because when you have small p-values, you're saying you can sort of investigate potentially important differences. So in this next example, we're going to quickly go through. We're going to look at HIV status. So over here, what if we want to compare HIV status? Up here, we compared age. So age is a continuous variable, whereas HIV status is categorical. So two values, one is HIV positive and 0 is HIV negative. And suppose we wanted to see whether there's a significant difference in HIV status between male and female patients. Now, because HIV is categorical instead of continuous, we use something called a chi-squared test. So again, before we perform any statistical test, it's good practice to form something called a null and alternative hypothesis. So over here, we can form a hypothesis to say our null hypothesis, or H0, is that proportion of patients with HIV among males is equal to the proportion of patients with HIV among females. And our alternative hypothesis, again, we can assume we have no prior knowledge about this data. We can use the two-tailed hypothesis just to say that proportion of patients with HIV among males is different, not equal to that among females. If we did have prior knowledge, so for example, if you're looking at some sort of treatment that you know improves clinically, you know that it'll improve a patient's outcomes, you can use that sort of prior knowledge to form the alternative hypothesis. So you'd be looking for an increase or a decrease in some characteristic. But for now, we'll assume we have no prior knowledge. There's no literature that tells us that HIV rates are different among males and females. So we're just using the two-tailed hypothesis. So luckily, R also has a really handy built-in function called chi-squared.test. First, what we're going to do is we'll quickly recode HIV status. So we're creating a variable called HIV status. So the case when HIV is equal to 1, HIV status is positive. And when HIV is 0, HIV status is negative. And again, I've got this little catch for any weird-looking values that'll automatically be turned into NA character. So if I run this, we'll get a little HIV data set, or a chi-square data set where there's an extra variable called HIV status. So over here now, let's pull our two variables of interest. We're simply pulling HIV status on its own and gender on its own. So over here, HIV status, we're saying select from the HIV data set. We're going to select HIV status over here. And if you guys want to see what it looks like, HIV status is just going to be a whole bunch of negative, positive, negative, positive. There we go. For all patients. Same with gender. So gender, we're going to select gender. There's just going to be a bunch of, I think, 1s and 2s. There we go. So finally, the chi-squared test. Over here, we're quite lucky because we don't have to specify as many things as the t-test. By default, the chi-squared test will test this alternative hypothesis. So by default, it tests the two-tailed hypothesis over here. And we don't have to worry about things being paired or not paired. That doesn't matter for this one. And the output is a lot simpler than the t-test output. So what's important here, again, is the p-value. So again, so if we have a p-value of 0.25, so let me ask you, is this statistically significant or not? Feel free to post it in the chat. Yeah, Ludovic's got it. It is not. So because the value isn't less than 0.05, it's not statistically significant. In sort of statistics terms, you would say something like, we don't have sufficient information to reject the null hypothesis, but we're going to talk in plain English just to say that there's no statistically significant correlation between gender and HIV status. So there's no difference between male patients and female patients in terms of HIV status. And then what we saw above is we gave it a try. So the GT summary package, TBL summary, allows us to print out p-values within the table itself. So over here, if we were to print out, I'll just quickly print out this table. Here we're actually able to print out, so everything we did above separately, we're able to print out directly in this table, so the p-value. So you can see important differences between female and male patients over here. You can see if there's any differences in age. Again, the p-value is massive, so no difference in age, no difference in CD4 counts, no difference in viral load, and no difference in HIV status either. So basically in this column, so if you were to do a table like this with your own data, and if you were to print out a table that had all these p-values, what you would look for is a low p-value. So you'd try to look for variables where the p-value is less than 0.05, and that would be something interesting. So that means, oh, this is cool, let me investigate this more because there is a difference between males and females here. So that was a pretty nice looking table. And there is a link for more details. So you can see something called, it uses something called a Wilcoxon rank sum test, and a chi-squared test, which we already used. So there's a little link for more details about what this test is, because as I mentioned, there's a whole bunch of statistical tests you can use. And according to this table, it looks like there is no statistically significant differences in any of the variables between male and female patients. And that's just a quick overview of t-tests and chi-squared tests. I see, I'm being mindful of the time actually. I feel maybe this might be a good place to pause because the next little topic is linear regression. So that can be maybe a bonus topic for people if you kind of go through the module on your own time. Basically, it introduces something called linear regression. So this whole time in the statistics module, we were looking to answer questions like, are there important differences in our data set? But for example, what if we were interested in understanding how much one variable influences another? So in a clinical context, something very simple to understand is smoking and lung cancer, but you can actually assign a estimate of effect. So how much does smoking influence your likelihood of getting lung cancer diagnosis? Or how often does a sedentary lifestyle, or how much does a sedentary lifestyle influence rates of cardiovascular disease? So in order to be able to assign a value for how much one variable interacts with or influences another variable, we use a statistical method called regression. And again, there's a bunch of different types of regression. What the rest of this module does is it goes through something called linear regression. And it goes through an example to answer that. But again, I'll pause for a second. I'll pause over there because I recognize we're running out of time, and I will let you go through this on your own time. And please do use the discussion boards on the course page if you have any questions or if you'd like us to expand on anything. But perhaps I'll pause there, and I'll hand it back over to Duncan to wrap up.
Okay, thank you so much, Ashna, for that session. And thank you so much to our participants for attending the courses up to this point. We have come to the end of our introduction to art training. We are hoping that there will be a continuation to this, but please let this not stop here. We can always interact on our R for Fun club in the discussion tab. Post your questions there. Let us continue coding. Let us continue interacting, and let us continue to get to know R better.